Thank you guys for joining us today. So today, I have a presentation on a new functionality that we're releasing actually this week that allows us to look at any really bacterial or viral genomes and how the nucleotide data represents changes in the proteins of different strains. And specifically, I'm going to be working with some COVID-19 strains, around 340 of them. And so the tools that I'm using are Megaline Pro, and it's part of a suite package that you guys have on site here. Is part of your portal. It's a site license that the group pays for here, so everybody has access to these tools. But what the tool is capable of doing is we can now load in a reference strain, and specifically I'm loading in the HU1 strain that came from Wuhan as a reference strain in a multiple sequence alignment. And then I'm loading in 334 other strains as well. And now if you notice, these are nucleotide data sets. And what this tool is going to help us do is look at how these nucleotide data sets represent changes in the protein instead of just the nucleotide changes. The reason we developed this workflow is because in talking with a lot of researchers, we noticed that a lot of people are spending a lot of time trying to convert and translate manually different nucleotide sequences to protein translations. And so we developed this workflow to help with that. And so if you notice, this right here is the HU1 strain that came originally from Wuhan. And one of the things I can do is I can rename the strain so it makes a little more sense. So I'm going to add a description to the default name, and I'm going to take the default name out. And then what it does is it lets me see that this is now the HU1 strain. If I hover over that, that's going to be labeled in that regard. Now, all these other strains here, these were all downloaded from NCBI, and they represent 334 of the over 1 million deposits that were made over the last few years to the GBK depository in NCBI. And we used our tool. I'm not going to show you how to use this, but we used our tool to download these sequences in GBK format. Now, it's critical that I'm using GBK files here, because if we look at one of these GBK files, I'm using an open source tool called Universal Viewer to view this. It has gene and CDS features. These gene and CDS features are critical for this analysis, so this won't work as well if you're using FASTA files. I just wanted to point that out, that it's required to have gene and CDS features here. But what the tool can do is we can load in this case, I've only done 334, but I've loaded up to like 10 or 20,000 of these, and it takes maybe an hour to do this. But I can set this as a reference. So I right click on that, set as a reference. Now it's choosing that original HU1 strain, which is the one from Wuhan as the reference strain. And then I go to align, and I align with MAFT. MAFT has a new reference-based aligner. None of the other ones have a reference-based aligner. They're all kind of de novo alignments. The MAFT aligner can use that strain that I marked as a reference as its reference strain. And so if I use this MAFT aligner, it takes around 30 seconds to do 334 of these. Now, it used to take us hours to do this before the MAFT reference aligner came out. And especially if you use Clustal W or Clustal Omega, it would take hours to just do this many, because these are rather large genomes. They're not huge, but it's 30,000 sequences times 300. But so in that amount of time, I can now have a reference-based multiple sequence alignment of those genomes, and you can see those here. Now, additionally, we have a tree capability where we can make neighbor joining and maximum likelihood trees. The maximum likelihood trees take longer, but they also can provide bootstrapping. So if you need confidence values in your clades, you can have those confidence values. But for today's demonstration, I'm just going to be doing a neighbor joining tree because it's fast and it'll show that it'll give a good idea on the capabilities. Now, while that's calculating the distance tree, I'm going to go up to this compute variance tab here. Now this is all brand new capabilities that were just released. In fact, the capabilities that I'm showing were kind of released in conjunction with this talk we're giving today. And it's going to be in the 17.4.2 version. And your group here does have access to all these tools, but you may not have access to this specific installer. So you can contact us if you need that installer, and we can get you this version. But if I now click the compute variance button, it just takes a few seconds to calculate all the nucleotide variants in all the strains here. Now, if I open this up and then I detach the window, it lets me have a full screen view of this. Now, if you notice, each one of these strains has specific SNP calls, and these are all non-coding. But if we go down, we can see that there's also non-synonymous calls right here and synonymous calls. Now, I'm interested in talking about the spike protein calls. So I'm going to go down and find the spike protein calls, which are down a bit right there. So here's all the spike protein calls that were made from these 334 genomes. Now, these are all in reference to the original HU1 Wuhan strain. And so you can notice that we have a residue. We also have a codon change that includes a residue change as well. So you see here, residue 19 had a mutation that was non-synonymous based on these SNP calls. Now, additionally, we now are just releasing this week. We have a delta change values where we can see how these non-synonymous calls are changing the protein and how that changes the charge, the PI, the hydropathy, the aliphatic index, and the instability index. Now, if we recall some of the more detrimental variants that occurred in the COVID outbreak, we can see that this caller has been able to find a majority of these calls. Now here's one that's actually a frame shift. It doesn't include any charge calls or PI calls with it. But if we keep scrolling down, we can see that these are some of the more well-known non-synonymous mutations to this genome. And these mutations were also found in some of the outbreaks that were in India a few years ago. The 452, the 478. And then also, if you notice, I'm scrolling down quickly. If there was any additional changes here, you would be able to see them because these codons get sorted alpha and numerically. So if we had a different call, these are all the same call. For some reason, all of these are identical calls. But we would be able to see these calls and how they're differential. So if we had a different 478 mutation here that had a different codon change, we would be able to see that as well. Now the 614 was also a really well-known variant in the COVID outbreak. And then also the 681 loss of that proline was also a really well-known variant. And what this represents, in just a few minutes, we found, as a company that deals with lots of researchers all over the world, we found that this workflow was a workflow that people were spending really a long time on. They were spending time translating these sequences from nucleotides to proteins, and they were doing this with custom Python scripts and Perl scripts. And so we identified this as one of the really downfalls of all the software we had seen. So we developed this workflow to help change these variant calls into non-synonymous protein calls, including the residue number. And then if you notice here, the charge change, the PI change, the hydropathy change, the aliphatic index, and the instability index. And the reason we are so interested in proteins is that all the work is to make the calls for the variants, but what really matters in our eyes is how that affects the protein, and specifically in this case, the spike protein. Now, I'm gonna minimize this window. It's gonna go back and dock. But what I also want to show you is we have a nice tree that was running in the background. And so now I have a really clear view of some of the variants and how they're differential and making different clades. So here's the original HU1 strain. And if you notice, all of these that that are to the left and close to this strain, those are all similar to that strain. But if we look at this clade here, that's a differential strain. And so what our tool can let us do is this tree is interactive. And I can click this original HU1 strain and then compare it to a differential strain, like with a single control click. I gotta do that again. So I did a single control click. Ooh, I did a shift click. So I do a single control click, and then I can do a right click and then do a really fast pairwise alignment. And then we have local, global, and semi-global. Now, semi-global, we're not going to use because that's really for like when you're aligning a primer to a much larger sequence. But in this case, I'm going to do a global Needleman-Wunsch alignment because that'll fix the endpoints of my alignment and give me a full alignment without any loss. A local alignment will look for the smallest, tightest alignment possible. And so I'm going to do a global. And also, if anybody wants to learn more about this, there's a little help button here that loads up our pairwise alignment help page. And you can go down and see what these different alignments do by clicking on some of these information links we have. And so I'm going to click here, and then we have a pairwise alignment that shows up. And then we can see all the different variants between this OP63044.1 strain and the original HU1 strain. Now, there is a bit of a secret trick here because our software is full of kind of Easter eggs, they call them. If you do a shift click and then do a control click, you get a really nice text-based output format that can go into Notepad in a really, I just like this type of format because it's kind of NCBI looking, and it's all text-based. And if you notice, you get identity changes and you get gap percentile from this report. Now, additionally, we have a really huge distance table that gets generated as part of the tree building process. And you can then see differences in this kind of distance map. It's a color-coded distance map. You can also change the coloring of the distance map by using some of these icons. Now, one additional thing that's really helpful is because we made the tree here, the tree has a specific order that is generated from all this data. But these sequences are not in that order. So if I go to tree and go to order sequences like tree, it'll then flip all the data around to match the tree. So if you notice, we have the 630057 at the top here. And now if I go to the top, the 630057 is also at the top. So we can reorder the sequences in the multiple sequence alignment to match the tree clades, which I think is really powerful. But so these workflows, they're really focused on allowing us to call these variants and know what protein changes are being made. And the reason for that, in our view, is because we're trying to go from SNP to structure. So we want to find SNPs, we want to know if they're non-synonymous, we want to make protein calls, and then we want to be able to model those into structures. So I'm going to quickly flip over here, and here's the spike protein with a closed RBDs, which just means these RBDs at the top haven't been cleaved yet, and they're still in the closed structure, so that hasn't opened up yet for attachment. Now, what we can do is we can take those variants that we just found, and I can go to a specific 681 region. Let's see here, 681 is actually right there. It's actually missing, unfortunately, in this structure, but I'll go to the 614 variant instead. So if you notice, I have 614 selected, and that correlates with this call right here, the D to G mutation. And then I can actually choose that D call, go to modeling, and then I can make a variant at that selection and add the G call to it. And what this does is this does a rotamer replacement and then lets us have a new model that incorporates the call that we found with that other workflow.
My apologies. We have 1 minute left.
And anyway, you guys, that's the power of the tools, is that we can quickly go from SNP to structure and then use our tools to model those structures and then have a new model with new rotamers that we can use for analysis.
Thank you so much.
You're welcome.